Hello everyone, welcome to this video, and we are going to continue our study of heat equation. So as I have told you in the last video, we are going to talk about how the separation of variable works here. Okay, so what are we basically looking at? See, let's say if you have a homogeneous rod. Homogeneous means it's basically is not the length is the width of the rod is basically the same everywhere, and the density is also essentially same. Yeah, so if you have a homogeneous rod of length L, let's say, yeah, okay, now, and we are just assuming that it is very thin. You think of it as a thread kind of thing. Yes, okay. Now what we are doing is this: we are just the heat, there will be some temperature distribution in the rod, right? And let's say that the heat is distributed equally in the cross section. Yeah, so basically let's say at the time t, the heat is distributed equally, right? There is no change in the, it's not like this part is hot, this part is not, right? Everything is in the same temperature kind of. Now if and of course this we are assuming it is very thin, so there will be a surface of the rod, and let's just assume it is insulated. Yeah, so we are assuming it is insulated. Why it is insulated? Because if it is insulated, then what happens is the temperature loss through the boundary is not there. Yes, so there is no change in the temperature around the boundary, so nothing gets escaped. You understand? Okay, then the temperature distribution of the rod. Okay, so the temperature distribution is given by this equation. Let me write down the equation. Ut equal to constant k times ux. This is one dimensional. Yes, since we are assuming it is thin enough, we can just assume that it is one dimensional. X lies between this one L, t positive, and u at the point 0 t is equals to 0. Again t is greater than equal to 0. U at the point L t is equals to 0. This is also for t greater than equal to 0, and u at x0 equals to f of x. Yes, this is for all x between 0 and L. Is it okay? See the temperature distribution. So essentially what we are saying is this is insulated. So at all time t, for every point x, so there is nothing which is going outside the boundary. So these are the boundary conditions, right? This is the initial condition. This is boundary condition, and this is the initial condition. So boundary condition says that there is nothing, no heat is exchanging. There is no exchange of heat on the boundary. So essentially that is the thing we assume that this is insulated. Clear? Okay. So now you see, if we assume, so we want to solve this, right? So if we assume the solution, so let's say our solution u of xt will look like this: capital X of x and capital T of t, some function of x times function of t. And let's just say this is non-zero. Why non-zero? Because otherwise f has to be 0. 0 is a solution of this one and both the boundary conditions, but 0 is not a solution of this. Yes, so we need that non-zero part. Of course it can be provided, f of 0 is equals to 0, that part should be taken care of, but generally speaking we are not looking for 0 solution, we are looking for a non-trivial solution. Okay, right. So if this is the case, let's call this as 1, this called boundary conditions, and 2 the initial conditions as 3. So from 1 what do you have is, you have x t prime equals to k x double prime of t. This is what we have. Very simple, right? We'll just differentiate this thing, and we are getting this if we put it in 1. Okay, so what does that imply? It will imply x double prime by x is equals to t prime by t, and this x, this is a function of x only, and this is a function of t only. Yeah, so there is no other way but for this thing to be a constant. Let's just call it minus alpha square. Okay, alpha is a positive constant. Okay, right. So why I am choosing minus alpha square and not plus alpha square? Because you can easily see that if x square by x equals to, let's say, a, which is positive, then x double prime minus ax, this is 0, right? and A is positive, huh? Then you can find out that with those boundary conditions, putting the boundary conditions, yeah, please check this part, yeah, why I am choosing it to be negative. If you put the boundary condition, what are the boundary conditions? See, it says that x0 equals to x at the point L is equals to 0. That's the boundary condition, right? If A is positive, x double prime minus ax, if you solve that equation, right, that will be e power a t ax type, right? The solution here, okay, so it will be some exponential solution, right? E power alpha 1x plus alpha 2x. So yeah, okay. Now the issue here is this: with these boundary conditions, x0 equals to xl equals to 0, that will actually imply x of x will be identical equals to 0. There is no other solution. Is this fine? So what happens is this: we cannot assume a to be positive in this case. Okay, so this is the idea of it. So that is why we're just assuming it to be minus alpha square, or alpha is a positive constant. Yes. Okay, so therefore what are the two equations which we have? We have x double prime plus alpha square x equals to 0. So that part you need to check, huh? By mistake I have somehow deleted it, but you need to check this, why we are taking it to be negative, why not positive, huh? And that's the idea. So just do it yourself and you will see it becomes clear. Okay, so and t prime plus alpha square kt is equals to 0, right? And what are the boundary conditions? If you look at the boundary conditions are u of 0 t, again it's exactly the same thing, right? U of 0 t equals to u of lt equals to 0, right? So this will actually imply that x at the point 0 equals to x at the point L is equals to 0. Yeah. So if we put that in this equation, what do you get? So therefore, let me do it in the next page. Therefore, if we put, what is our equation then? X square plus alpha square times x equals to 0, and what you have, x0 equals to x of L equals to 0. Let's just call it, I don't know, maybe 4, huh? Let's call it 4. Now you know that any solution of this thing, x of t, how does it look like? It looks like a cosine alpha x plus b sine alpha x. Clear? This is the solution. And since x0 equals to 0, that will imply, if you put it here, a is going to be 0. Clear? Now again, you can see that since x of L is equals to 0, that will imply that b sine of alpha L is equals to 0, right? Which is equals to sine of n pi, and n is in z. Clear? Okay, so if this is the case, then what you have is sorry, that b won't be there. B won't be there. The sine of alpha is sine of n pi. Yes. See, if you put it here, it becomes b sine of alpha L is equals to 0, right? Since b is not 0, because a is already 0, if b is 0, then that will give you the 0 solution for this problem. We don't want that. So what do you, because otherwise the whole problem solution becomes 0, right? We don't want that. Okay, so b is non-zero. Since b is non-zero, we can just delete it out. So we are left out with sine of alpha L is 0. So that will imply 0 is sine of n pi. So sine of alpha L equals to sine of n pi, which will actually imply that what is going to imply? It is going to imply that alpha is equals to n pi by L, right? And you can take n to be n also, absolutely no issue. So essentially it will be the same thing, huh? So I'm just taking n to be n. Yes, no issues here. Okay, now if you substitute that in the equation, what do you get? Therefore, the eigenvalues which you are going to get, eigenvalues, if you substitute the eigenvalues, substituting the eigenvalues of the eigenfunctions essentially, if you substitute the eigenvalues, the eigenfunctions which you are going to get, eigenfunctions are given by xn of x, yes, and that is nothing but b of n sine of n pi x by L. Is it okay? Yeah, so you get like this thing, countable set of solutions. Okay, now we have another equation. See, this is like just x part, right? There is this t part, t prime plus alpha square kt equals to 0. Again, t prime plus alpha square k times t is equals to 0. Is it okay? So what does that imply? You can easily see that that will imply t of t is nothing but c times e power minus alpha square kt. Clear? Now you see this alpha square, we already know what alpha is, so you can just put it that in the equation, and hence, and so we'll have for each n, t and t will be a solution. So that is nothing but a constant times e power, constant depending on n of course, e power minus n pi by l square of that times t. Is it okay? What is the k part? K is there. K. Okay. K is there. Okay. So that is there. So therefore, what are the non-trivial solutions? Therefore, the non-trivial solutions, the solutions un of xt, non-trivial solutions un of xt, that will look like this: xn of x times tn of t. Clear? Okay, so what is xn of x? Xn of x is some constant times sine, right? So I will just put it as a constant an. Okay, an. So you see, xn is bn times sine, and tn is cn times this. So bn times cn, I'm just writing it to be n. Bn times cn, let's say it is n. Where? Okay, and this looks like an times e power minus n pi by l square k times t, and then sine of n pi x by l. This is the solution for n equals to 1, 2, 3, it goes on. I hope this is clear. Right, now we have the superposition principle, right? What is it? That this un, they are solutions for each n. So u of xt, that will be our solution, which is nothing but defined as summation n equals to 1 to infinity, and then un of xt. Yes, that is nothing but summation n equals to 1 to infinity, okay, an, that constant, times e power minus n pi by l square times t, and then sine of n pi x by l. Yes, so that is what we are getting, right? Now you remember that, what is this thing? But that condition is right. There's this, yes, there's this initial condition, right? So u of x0 equals to f of x, that is given to us, right? So we have to now utilize this fact. Okay, so since f of x equals to u of x0, so what is this condition? At time t equals to 0. So this is the initial condition. Yes, okay, so this is given by summation n equals to 1 to infinity an sine of n pi x by l. Yeah, by the way, this is, see, we are using Fourier series here, right? And this is the exact thing which actually helped Fourier to deduce this Fourier series. The Fourier series part, Fourier explained this thing, right? He has actually discovered this part, and the thing is, this he did while studying the seat equation. He wanted to solve this thing, yeah, and that is how he got it. Okay, so now you do realize that you have a function which you want to write it in terms of sine. So basically Fourier sine series, you remember, yeah, and so if you do that, what is the an? Therefore ans will be 2 by l, 0 to l, 2 is minus l to l, so that becomes t to l, f of x sine of n pi x by l dx. Yes, we talked about it. So this is via Fourier sine series. Yeah, sine series. If you don't remember, please go back to those videos and look at it. Okay, so if you have this thing, hence the original solution, the solution which you are actually interested in, u of xt, those will look like this. They are summation n equals to 1 to infinity. Yes, and then you have this ans, which is 2 by l, 0 to l, f of x sine of n pi x by l dx, n pi x by l, one second, dx, right? I hope I am writing it correctly. Yeah. Okay, and then exponential of minus n pi by l square times k times t. Okay, and then sine of n pi x by l. Yes, so this is the solution, formal solution of the heat conduction problem. Is it okay? right? Yes, so this is exactly, I mean, the problem which Fourier discovered. Yes, now a small thing. Yes, let's say that you see, there are two ends to the rod, right? This end, this end. Let's say that this end, the solution, we are assuming that the temperature at the one end is 0, and the temperature at another end is not 0, but it is held at constant. So basically, the equation in this case looks like this: minus u x equals to 0. Okay, so this is a small note. Let's just put it this way: u of the xt, sorry, 0t, u of 0t, this is of course 0. Yeah, we are assuming that there is no heat exchange there, but u of lt, at any time t, that is equals to u naught. So basically the temperature is constant on the other end. It means that a temperature at one end of the rod is held constant. Okay, constant. Okay, and if that is the case, then u of lt equals to u naught. Yes, then the problem is ut equals minus uxx equals to, so forget about k. If you want, you can just put it in k, but the thing is, for now let's just, or maybe I can put it, doesn't matter, k times uxx. And then you have this initial condition, u of x0 equals to f of x. Now this is similar sort of problem here, just that one part is at 0, one part is at u naught. Now how do you do it? See, this is a small trick which I am going to show you, and you can use this trick in many different places also. Clear? So this trick is used even for other problems, not exactly for the not explicitly for heat equation. Yeah. So let's say let u of xt, yeah, that's the solution of this equation, right? I don't know, maybe let's put this equation as star. The whole thing is star. Okay, so let u of xt, that is your solution, and that we want to break that solution up into two parts. One part is v of xt, and then there is another part which is taking into account u naught. So I am writing it to be u naught x by L. Is it okay? Now you see, if we substitute this in the equation, what happens? U of t is nothing but v of t. This is independent of t, and u of x, okay, x, if you do it, it becomes v of xx. See, this is just a first order term in x, right? So if you're taking two derivative, it doesn't have it doesn't contribute anything. So uxx is vxx. Yes, so hence the original problem in terms of vxx, if you want to write, it becomes vt equals to k times vxx. Clear? And this is for 0 less than x less than L and t positive. Yes, and v at 0t, this is equals to v at lt, this is equals to 0. You see, right? See, lt, if you put it, it becomes, where is it? Yeah, see, u of lt is equals to u naught, right? Yeah, and then that is equals to v of lt plus u naught, x is L, right? L by L. So you see, if they get cancelled, this u naught and u naught get cancelled, so v becomes 0. Yes, okay, so that's the idea. See, this change of variable is done in such a way that you can actually write it in this particular format. Yeah, yes. So what we'll do is this. So I hope you understood why this is a small trick, but this trick works. Why this works? Okay, and of course, what is v of x0? X0, this is nothing but, you see, it does it just shifts x, right? So f of x minus u naught of x by L. This is for 0 less than x less than L. Yes. Now we are in our original problem, so you know what the solution is. Okay, and we just find out what v is and then add u naught of x by L with it, then that will be your u. So I am not doing this part, I am just writing it out. Therefore u of xt is, see, this problem is our original problem, just the problem which we already did. So we can solve it. You can solve this problem. Yeah, this is your new g, let's say, yeah, or new f, whatever you want to call it. So anyways, now you just solve that problem and you have your answer. So let me just put it here. It is n equals to 1 to infinity. See, it is v of xt. V of xt is essentially this particular thing. Here f will be replaced by f minus this thing, u naught x by L, that will. And again everything is same, right? So you see it becomes 2 by L 0 to L f of tau minus u naught tau by L. Okay, and where is it? I have missed something, no? Sine. Sorry. The sine part I did not write. So this is sine of, and then you have n pi tau by L and d tau. So this thing, this part, yes, this is the Fourier part, remember, and then exponential of that part does not change, n pi by L square times k t. Okay, and then the sine part, the x part is there, sine of n pi x by L. Okay, plus this additional term is there, you see, u naught x by L. Okay, so then this is your solution. Is this okay? So this is how you solve it. So it is very easy. It's absolutely no issues. Okay, so with this, what we are going to do now is I am going to show you that that uniqueness we talked about using this thing, Maxwell principle, right? But I did not give you a proof of it. But the one dimensional heat equation, I just gave you some ideas. Of course, that is also not a proof. I just assumed something and I just showed you that something of that manner should work. Now I am going to give you the proof of it. Okay, so uniqueness theorem. So let us understand what uniqueness theorem says. So it says that let u of xt, okay, is continuously differentiable function, at least C1, yeah, or maybe you can take C2, sorry, twice continuously differentiable, let's take twice continuously differentiable function. Okay, satisfying ut equals to k uxx. Okay, and this is between, x is between 0 and L and t is positive. Yes, okay, with the initial data, what is the initial data? U of x0 equals to f of x for 0 less than x less than L, and u of 0t equals to u of lt equals to 0 for t greater than equals 0. Is it okay? If this happens, then the solution is unique. Okay, see what this problem basically says is, if you have a initial so sorry, once again I did a mistake here. This is the, I should write it with this data, this is your initial condition. I see initial condition because this condition gives that t equals to 0, and this is your boundary condition. Okay, okay, sorry about it. Okay, so it says that basically the solution is unique, but please remember this thing here, for the uniqueness you have to have x is bounded in a bounded region. Without that we can't prove it. Okay, so, and it's not, I mean, it's not true also in unbounded domains. So in last video we have always talked about it. In last video also, it is not true. Okay, so let's say for the proof, let u1 and u2 are both solutions. u1 and u2 are both solutions. Okay, so if they are both solutions, then w, which is, or let's say v of xt doesn't really matter, is given by u1 of xt minus u2 of xt. This solves this particular problem. Vt equals to k times vxx. You can see this very easily, right? And where does it solve? X is between 0 and L and t is greater than 0. V of 0t, yeah, equals to v of lt equals to 0. Yeah, see, this does not have to be 0. You can see, right? If it is something a function of t also, what happens is this difference u1 and u2 both satisfies those things, the difference will be 0. So you can actually change this boundary condition to even g of t and still this will hold. Okay, so no issues here, but let's just keep it simple. Yes. Okay, so this is for t greater than equal 0, and then v of x0, this is nothing but 0 for 0 less than x less than L. Yes, that's the thing. Now you see, for this system, this is a system, right? And so what we need to do is we will define something called the energy function. Remember, we did it similar sort of thing for a wave equation. So we define an energy function like J of t. What is the energy? The energy of the system in this case is 1 by 2k pi 0 to 1 v square dx. Okay, right. This is true. What we have is we need to differentiate this thing with respect to t. So therefore, j prime of t, yeah, we can differentiate it. Why? Because v is continuous function. If you are integrating a continuous function, sorry, this is L. You are integrating the continuous function, then also what you are going to get is essentially a continuous function. So essentially what we are doing is, you see, I am integrating it with respect to x. So v is a function of both x and t. Here I am integrating it with respect to x. So for any fixed t, essentially you are getting something in you are getting some integral with respect to x. Yes, and what happens is, and then that once you make the t run towards whatever I mean it is defined on, let's say 0 and some capital T, then this becomes a function of t. Is it okay? Once you fix a t, v of x t is just a function of x. That function you are integrating with respect to x, and then for a fixed t, that is a number, right? So now I'm running between whatever t is defined. So now j prime t in this case is nothing but 1 by k, and then 0 to L v t dx. Is it okay? And now that is nothing but 0 to 1 vxx dx. I hope this is clear. Okay, now if you integrate by parts, you know what to do here, integration by parts. So what is this thing? This is nothing but vx defined on 0 to L, exactly the same thing which we did in the wave equation, right? Minus 0 to L vx square. You know integration by parts, you just do this integration by parts, right? Now you see, it's exactly like wave equation again. Since v of 0t equals to v of lt equals to 0, okay, therefore j prime of t is equals to minus 0 to L vx square dx. Is it okay? Okay, you see this part is 0, so this is the only thing which is remaining. Yes, now if you look at the condition, you see v at the point x0 is f of x. Okay, so from this condition what do you have is, therefore since v at x0, that is nothing but 0. Clear? Therefore what we have is j of 0 has to be equals to 0. Is this okay? See, this is a positive term. You have to understand this thing. Vx, whatever Vx is, Vx square is a positive term, and you are integrating a positive term which remains positive. So what you have is this j prime t is actually going to be less than equals to 0. It has to. And j prime t, you understand what I'm saying, right? And you see j of t, yeah, yes, and you see j of t, yeah, this is always assumed to be positive. Yes, see, one, okay, let me put it this way. See, since j of t, if you look at j prime of t, j prime t, this is a positive term, right? So if you are taking the integral of a positive term, that becomes positive, and there is a negative term, so essentially j prime t is nothing but less than equals 0, yeah, for all time t greater than 0. Is it okay? Again, so essentially what does it say? It says that j of t is non-increasing in t, right? So that will imply the j is non-increasing in t, okay. Again, you see j of 0, if you want to calculate it, j of 0 is nothing but 0. Yeah, why? because since v of x0 at the time p equals to v of x0, that is nothing but 0. Is this okay? Yeah. You remember? Where is it? Yeah, see? V of x0 is 0, right? For all x between 0 and L. And that is why, since v of x0 is 0, see, what is j of t? J of t of 0 equals to integral 1 by 2k 0 to L v of x t equals to 0 square of that dt, right? So v of x0 is 0. So essentially j of 0 becomes 0. Is it okay? I hope the calculation is fine here. Okay. So what do you have? J of 0 is 0 and j is non-increasing in time. Yes. What does that say? But again, j is, you see, j is a positive number. That is also true. K is assumed to be positive. Yes. Here I should actually write it. No, I did not write it. K is always assumed to be positive here. Yes. Okay. So what am I here? Yes. So see, j is always positive term. Huh? So again, j of t is always greater than equal 0. Is it okay? J of 0 is 0. J of t is always greater than equal 0 for all t. Again, j is non-increasing. What does that imply? That will imply that j of t has to be 0. That will imply j of t has to be 0 for all t. For all t, which will imply that v of xt has to be identical equals to 0. Yes, for x between 0 and L and t positive. I hope this is clear. Why? Because if j is 0, you see, it becomes that the integral of v square has to be 0. So v has to be 0, right? There is no other way. So if v is 0, that will imply u1 has to be equivalent to u2. I hope this is clear. Yes. If it is not clear, what I am asking you is, please go back and just look at the proof again. Yeah, this is a very interesting proof, and this actually j of t, this is what are you getting it? We are just getting it from the energy functional of it. So this is called the energy functional, energy of the system. This represents functional. Okay, right. So this actually shows that if you have the heat equation in a bounded domain 0 x between 0 and L, then you always have the solution. If there is a solution, that has to be unique. Is it okay? So with this, I am going to end this video. Thank you.